In this video, we will learn about logarithmic and exponential derivatives. Now, in my last video, I went over what I said to be all differentiation rules that you will need to know when you're taking derivatives, but I kind of lied. These two rules are also necessary to know if you want to know how to derive any sort of function. So I will talk about deriving logarithmic functions, that would be the natural log, and other logarithms. And I will get to exponential derivatives with base e and other exponential functions with bases other than e. So let's get started. So first off, the natural log. The first thing you need to know, and probably the most important, is that the derivative of a function that is the natural log of x, this is equal to 1 over x. And intuitively, this makes sense. If you think of what these graphs look like visually, at least on the positive reals, because the positive reals is the domain of natural log of x. So if I were to kind of sketch out the natural log of x, it looks something like this, right? It's the inverse of the exponential function. It looks something like that. If you look at the instantaneous slope, it starts out very, very large when x is very small. And as x gets larger, the instantaneous slope gets smaller and smaller and smaller and approaches 0. And if we were to look at the graph 1 over x, just the positive reals, looks like this. Starts out very, very large when x is very, very small. And as x gets larger and larger, it decreases and approaches 0. So visually and intuitively, 1 over x looks like it should and is the derivative of the natural log of x. So, what if we had the natural log of something? What if we want to find the derivative of the natural log of something other than just x? So we can call it u, where u is a function of x. Now, it turns out this is equal to u prime, the derivative of u, over u itself. So this would be the derivative if u is something other than x. And if we plug in x for u, we do get 1 over x because the derivative of x is 1. So that turns out to just be 1 over x. Now, the way we find this formula, the way we got this, is we can apply the chain rule. So we remember that the derivative, so in this case, if we can remember the chain rule, it would be the derivative of f of u, where u is some function of x. The derivative of f of u would be equal to f prime of u times u prime. So in this case, f of u is natural log of u. So that would mean that f prime of u is 1 over u. So applying the chain rule directly, so if we were to find the derivative of f of u, we're calling it equal to natural log of u. From the chain rule, we get this is equal to f prime of u times u prime, right? Now, f prime of u is 1 over u. So this is equal to 1 over u times u prime. And this is just equal to u prime over u. So that is where this formula or this derivative comes from for the natural log of u, where u can be any function of x. So I'll give an example. So the natural log of, let's say we have a function, f of x, is equal to the natural log of x cubed minus 2x. Now the derivative of this would be equal to the derivative of the inner function, which is 3x squared minus 2 over the inner function itself, which is x cubed minus 2x. So this would be the derivative of this function. Not too hard. Now, so that's that. Now we can get into other logarithms. So when I say other logarithms, I mean logarithms that have base other than e. So the base of the natural log is e, and that makes things very convenient because it works out the derivative of the natural log of x is 1 over x. However, that is not the case when the base is something other than e. So it turns out that if we want to find the derivative of a function of the form log base u of v, where u and v are both functions of x, it turns out, I'll just give you the formula right off the bat, and then I will show you how I derive the formula. This is equal to the natural log of u times v prime over v minus the natural log of v times u prime over u. And then all of this over the natural log of u squared. So this would be the derivative of log base u of v. And you may be thinking, this looks an awful lot like the quotient rule. And you'd be right. That's exactly how we derive this. So right now I will show you how to derive that formula. So if we have a function y equals log base u of v, first off, we can do a change of base to get convert everything to base e. So that is equal to natural log of v over natural log of u. That is how the change of base formula works. It would be the natural or the log with the new base of v, and then all of that divided by the log of the new base of u. So that is how we would apply the change of base formula. So y is equal to natural log of v over natural log of u. Now we know the derivative of natural log of v. We know the derivative of natural log of u, and it is in the form of a quotient or a fraction. So we can apply the quotient rule. So we get that the derivative dy dx is equal to low d high, right? Low d high minus high d low. Don't forget to square the low. So low is natural log of u. D high, the derivative of the numerator, that would be v prime over v, minus high d low. High is natural log of v. And then d low, the derivative of the denominator, would be u prime over u. And then don't forget to square the low all over the denominator squared, which is natural log squared. So that is where this formula comes from. Okay, now I will do an example with this. Other logs. So let's see if we have a function y equals log base x to the fourth of tangent of x. Now we want to find what is dy dx. What is the derivative of this function? Okay, so first let's do a change of base to get a natural log. So y would be equal to natural log of tangent of x over natural log of x to the fourth. Now we can take the derivative to get dy dx. So that would be low d high minus high d low. Don't forget to square the low. Low is natural log of x to the fourth. D high, that would be the derivative of the natural log of tangent x. That would be secant squared x. The derivative of tangent is secant squared x over the inner function itself over tangent x. And then minus high d low. So high, that would just be the numerator. Natural log of tangent of x. And then d low, the derivative of the numerator, the derivative of natural log of x to the fourth. The derivative of the natural log of x to the fourth is 4x cubed over x to the fourth. All of this over natural log of x to the fourth squared. So this should be the derivative. Now we can simplify some things. One thing that we can simplify is this radical. Radical right here. This should just be equal to 4 over x. So that is one way we can simplify this. I'm sure there are other algebraic ways to simplify this fraction, but this would be an equivalent answer to the derivative of this function. Okay. That's that. 4x. Okay, let's move on. Let's do exponentials with base e. Okay, so more specifically, the derivative of the function e to the x. Now, e, Euler's number, it is an irrational number, and its value is such that its derivative is itself. So the derivative of e to the x is e to the x, which make things very convenient. That is one of the many cool properties about Euler's number. That also means that the integral, when you learn about integrals and antiderivatives, the integral of e to the x is also e to the x. So, yeah, e to the x is pretty nice. So that is the main thing to remember, the main thing to know. The derivative of e to the x is e to the x. Now, what about functions where it's not just x? So what if it's like e to the x squared or e to the sine of x? What if it's e to the something other than just x? So the derivative of a function of the form e, and then I'm just going to say to the u, where u is a function of x. This is equal to e to the u times u prime. And this is very similar to the natural log of u. We can apply the chain rule to find this. So if we set, say, f of u equal to e to the u, that would mean that f prime of u is also equal to e to the u. So applying the chain rule, the derivative of f of u excuse me, is equal to f prime of u times u prime. And we just said that we just found that f prime of u is e to the u. So this is just equal to e to the u times u prime. So that's where this comes from. And yeah, so let's do an example. So if we have, let's say we have a function f of x. I've been switching using y and f of x. It's somewhat interchangeable. I suppose if you have f of x, you know it's a function, so it will pass the vertical line test, and so on. Yeah, but you can still differentiate the same way. So if we have f of x is equal to e to the cosine of x, doing some more trig stuff, it's good to know your trig derivatives. So if we want to find f prime of x, this will be equal to e to the cosine of x, just rewrite it, and then times the derivative of the exponent. The exponent is cosine of x. The derivative of cosine of x is negative sine of x. So we get that f prime of x is equal to negative sine of x times e to the cosine x. So that's a little example of this exponential function, or these kinds of exponential functions. Okay. Now going to other exponentials. So there are other exponential functions, and not all of them have a base e. And it's important to know how to derive these also. So if we have, again, I'll just give you the formula right off the bat, and then I will show you exactly how I got the formula. Oops, let's do not this. So we find the derivative of the function of the form u to the v, where u and v are both functions of x. In the previous slide, the case that we were dealing with was when u was just equal to e, the constant function of e. But if the base is something other than e, like say like x squared or sine of x or x plus 5, some function of x, and so is v, turns out that the derivative of this is equal to u to the v times v prime times ln of u plus v times u prime over u. So yeah, that is the formula for this kind of function, and I will now show you how to get this formula, how to derive it. It's not super necessary to memorize all of these formulas. I'd say it's most importantly to memorize that the derivative of the natural log of x is 1 over x, and then the natural log, and then the derivative of e to the x is e to the x. Those two things I would commit to memory. Other than that, just knowing how to apply the chain rule, and then the quotient rule, and then in this case, the product rule. If you know all of those things thoroughly, you would be able to derive what you need to for these kinds of examples. So if I have, so back to this, if I have, say, y equals u to the v, where u and v are both functions of x, I want to find dy dx. I want to derive. But I don't know how to derive u to the v, so I'm going to take the log, or the natural log of both sides. We can do this. Natural log of y is equal to natural log of u to the v. Now, we know that using log rules, this side, the right side, natural log of u to the v, can be rewritten as, or I'll just rewrite both sides. Natural log of y can rewrite the right side as v times the natural log of u. We could bring down that v. Now, on the right side, we have a product of two things we know how to take the derivative of. And on the left side, we have something of y, but we know how to take the derivative of the natural log. So we can do something called implicit differentiation, and we do it like this. So we take the derivative of the left side. The derivative of the natural log of y is 1 over y, and then when you're doing implicit differentiation, you want to multiply this by a dy dx. That is where the derivative comes in. And then that would be the left side. And on the right side, we have a product of two factors. So the derivative would be v prime, the derivative of the first factor, times ln u, and then plus v, but just rewriting the first factor here, times the derivative of the second factor, which would be u prime over u. Now we can multiply both sides by y to bring that y over. I get dy dx, just to solve for the dy dx, is equal to y times v prime natural log of u plus v times u prime over u. Now we know what y is. Y is u to the v. So we can rewrite this as dy dx is equal to u to the v times v prime natural log of u plus v times u prime over u. Excuse me. So, yep, that is how we get the derivative. Let me just check, make sure everything's good. Yeah, this is correct. So we can do one more example. This will be our longest example. Hopefully I don't run out of space on this paper. So we'll do another example, our last example now. So considering what we just did, if we have, say, let's do this. If we have, say, y is equal to cosecant x raised to the x to the fifth power, what would be the derivative of this? What would dy dx be? Now we can do the same thing. You could just do the formula and plug and chug, but I think it's best to work through it. So the first step we did was take the natural log of both sides. Natural log of y equals natural log of cosecant x to the x to the fifth. Natural log. Make sure I put these parentheses in the right place. No. Yeah, so it wouldn't be the cosecant of the x to the x to the fifth. It would be cosecant x all raised to the x to the fifth. So these should be the correct parentheses placements. So we can take the natural log of both sides. Now we can do the log rule on the right side. Here on the left side, we still have natural log of y. And on the right side, we can bring down the x to the fifth. Get x to the fifth times natural log of cosecant x. Now we can do some implicit differentiation. So on the left side, we have the derivative of natural log of y is 1 over y, or with respect to x, I should say. The derivative of natural log of y with respect to x is 1 over y times dy dx. And this will be equal to, we can do the product rule. So we do the derivative of the first factor, which is 5x to the fourth, and then we multiply it by the second factor, natural log of cosecant x. And then we add, we can just rewrite the first factor, x to the fifth, and then take the derivative of the second factor. That would be negative cosecant x cotangent x over the inner function itself over cosecant x. Now, right off the bat, you can see that we can simplify this fraction, and I will do that momentarily. So I'm going to combine two steps. I'm going to bring over the y, so I'm just going to solve for the dy dx. Dy dx equals y times the right side, 5x to the fourth, times natural log of cosecant x, and then bring the minus, so I'll do a minus, and then the x to the fifth times cotangent x. because the cosecants cancel. So we have this dy dx is equal to this. Now we know what y is. Y is cosecant x all to the x to the fifth power. So we can rewrite that to get dy dx is equal to cosecant x to the x to the fifth power times 5x to the fourth times the natural log of cosecant x minus x to the fifth times cotangent x. Yep, a little ugly, but nonetheless, we got there. So that would be the derivative of this y. That would be this dy dx. That is my last example.